Okay, so once again you are most welcome. My name is Mtanda Samir. Please, we are in for our UCE mock physics, specifically Jjeb, and we are now continuing with our series. This time around we are in for item 3. Okay, please, you check in the playlist, you have right here from item 1, item 2, and right here we are on item 3. Please, we promise more to come, more to come. Okay, now just like we had the other items, this is very enticing, and please, it has very many learning points. Just know that anyway, it's an interesting one. That's why, okay, it has been our culture that we post almost every day, but due to the details in this item 3, we had to at least skip a day, and that's why we have chosen to upload it today. So please be there to watch it to the end such that you don't miss out any bit of it. My name is Mtanda Samir once again. Okay, so without wasting time, let's proceed. Okay, yeah, again we remind you to subscribe to the channel. Please, I told you that for whoever has not subscribed to the channel, you may even miss out item 4, item 5, and item 6, because it is after I've subscribed that now you'll be able to watch. Okay, I told you that the YouTube algorithm allows us to limit people to limit our videos to strictly our subscribers, and of course sooner or later I'll be doing that. It is a disservice indeed. I kept on telling you this, that you keep watching without subscribing. Take your time, take the initiative to subscribe such that you don't miss out item 4, 5, and 6. Anyway, we proceed. Okay, so right here we are good to go. We are good to go. Get some letter pen here. So the saying, your school has gone for a study trip to a newly opened space observatory station, SOS, in your country, and every student is allowed to go with one parent, a way of engaging the community in knowledge enlightenment. At the station is the station manager, but the station manager traveled with his assistant abroad for space exploratory workshop. The instructor's manual at the SOS. The instructor's manual at the SOS, remember we have that as the space observatory station, gives two parents each a chance to ask one question, and we're all allowed to ask the following questions. Parent A: what causes rise and fall of water levels in seas and oceans? Anyway, good question. I see it's a very good question. Parent B: how is it possible for someone in Uganda to talk to a relative in USA through a cell phone? Of course, that's parent A. Parent B: what if when you are parent C? What will you ask in the long run? Anyway, as you think about that, let's proceed. So in the same manual, things to talk about are an astronomical unit, AU, a light year, and life cycle of a star. Oh, bit interesting, life cycle of a star. Anyway, just give a flashback. Do you think you really know a life cycle of a star? Okay, if you think you know, better watch it such that you really see that there is something strange or something new you're going to add up into this. All right, proceeding. So let's see. So people are shocked on seeing a statement: the sun's radius is 109 times that of the earth, and the sun's mass is 3.30 times 10 power 5, or you can read as 3.30 exponent 5 times that of the earth. Anyway, shall analyze that later. The station manager does not have the knowledge on space physics and communications. That's really bad. Hint: the average density of earth is 5,500 kilograms per meters cubed. The volume of the sphere is, of course, we all know formula for volume of the sphere is 4 over 3 pi r cubed. Task, we move the same. You have been asked to volunteer as a station instructor to guide the tourists since you have the knowledge on space physics. Okay, what a pleasure. Anyway, it is a honor even. But it can be a honor if you know what to do right here. So, but just know, if you're a student in senior 4, you already have a post to serve. You are the station instructor. So be there to defend yourself. Part A: distinguish between a light year and astronomical unit. You see? Remember number 2, respond to the questions asked by parents A and parent B. Okay. So let's see. We finalize here. Lastly, part C the same. Describe the life cycle of stars. In fact, part B, describe the life cycle of stars. Part C, help the tourists to establish the average density of the sun. Then lastly, importance of studying astrophysics. Alright, good. So without wasting time, let's go and make the quick analysis. Okay, there's a pen, maybe. Get this marker here. So the saying here, Roman number 1, distinguish between a light year and an astronomical unit. I think let's get this answered first of all, which is our Roman number 1. Let's go and have it answered already. Okay. So with this, you'll have this. First of all, part A Roman number 1, we are getting it answered. You must all know that what we call a light year is the distance traveled by light in 1 year. Now, what we call a light year is just like one light year. So, distance traveled by light in 1 year. Meanwhile, what we call an astronomical unit is simply the average distance between the Earth and the Sun. Okay, now, maybe we go pictorial a little bit. So, to try to go through this for you. Now, this one here is our Sun. If you can look into that, that is our Sun. Now, the distance traveled by light from the Sun. Okay, the distance traveled by the light from the Sun. Okay, in 1 year, we call it a light year. Now look, from the Sun, next planet is Mercury, and next planet is Venus, and the next planet is our mighty Earth. Okay, our beloved planet Earth. So, once light is moving, say for example, you have light going. Anyway, allow me to resolve this. So, maybe our light is going, and maybe it's at that interval, and it has taken 1 year. Once it takes 1 year to reach that interval, we call it a light year. Then what about an astronomical unit? Now, astronomical unit is the average distance between the Earth and the Sun. So you all know that the Sun orbits around, rather the Earth orbits around the Sun, meaning if this is our Sun, this Earth keeps on moving in that order. Just imagine that is circular, a normal circle. So you know that at a certain time the Earth can be here, at a certain time the Earth can be here, at a certain time the Earth can be there, at a certain time the Earth can be right there. Okay, now realize that now, say for example, let's consider here we are going to look at this situation where we consider if the Earth is at this level and if the Earth is at this level, a bit opposite to each other. So realize that when you count, say for example, the distance of the Earth is right here. Okay, if you can look at that, okay, 152 okay, 152,100,000 kilometers. What about here? We have this average here, the distance from here up here to this, distance from here up here to this. I mean that when you add this plus that, then you divide by 2. The answer you get there is what we call the astronomical unit. So it's simply the average distance between the Earth and the Sun. And I've showed you how that comes about. The astronomical unit, we simply add and divide by 2. Okay, as simple as that. So with that, we have, please have said you add this plus this, you divide by 2. Then the answer you get is what we call an astronomical unit, which is simply the average distance between the Earth and the Sun. This is our Sun. And of course, this is our Earth, and that's our Earth right there. Okay, with that, let's, I think, proceed. We go to another part. And right here we have, okay, get some ink here. The saying, Roman number 2, respond to the questions asked by parents A and B. Okay, by the way, we have to respond to the questions asked by parents A and B. But what questions do you think these people asked? Let's go and make some analysis. Remember, we are the station instructors. So, parent A asked, what causes the rise and fall of water levels in seas and oceans? Let's go and answer that first of all. What causes the rise and fall of water levels in oceans and seas? Now, before we go that, you all know our culture is, we first of all go pictorial. Now, trying to go pictorial, here we go. Okay, looking at this, please, what you must first of all know, there was a law of gravitation, okay, of which this was revealed by Sir Isaac Newton. You realize that the law of gravitation says that if you have a body of like the kind and have another small body like this, they say that any two bodies which exist in the universe, these two bodies here have a force of attraction between them. But this mass here is big and this mass here is small. If you look at that, now what happens is this big mass here will pull this small mass to itself. So there is a force of attraction between any two bodies on the universe. Okay, I hope you can really note that. So just imagine that, just like you are yourself right there, and maybe your house right there, or your class, if you're a student, your class. Now there is always a force of attraction between you. So since the house is more heavier than you, the house pulls you towards it. But however, please, what is again said about this force is that this force cannot easily be felt. You can't feel it. Of course, just know, you can't just be there and feel like this building is pulling me. But just know that force exists, and that force we call it gravitational force. Gravitational force. Okay. Now, that gravitational force is by far different from force of gravity, because force of gravity pulls downwards, but this gravitational force exists between any two bodies. Like say for example, you have maybe, okay, I already, okay, still give an example again, like you're just right there, you're the one there, and maybe there is okay, right here we have a what? We have a car. This is our car. Maybe there is a force of attraction. Since the car is very heavy, the car pulls you towards itself, but we have said you cannot feel that force really. Now if you have understood that, we bring the same issue that we have here our moon. Okay, we're explaining how the tides come about in the seas and oceans. We have our moon right here. Allow me right there. So this is our moon, and this is our earth. Now what should you expect out of this? So if this is our earth, then what must you expect? What must you expect here is that it acts the same way that the moon, they have a force of attraction towards them. They have a force of attraction towards them. Now I find that the moon the gravitational force from the moon, okay? So you say that the gravitational pull of the moon on the ocean. So you realize that since these two have a force of attraction between them, from this expression I given up here, you realize that, because of this, maybe I first level a bit. Now there is a force of attraction from the moon has got a gravitational pull onto objects on Earth. But of course, remember, the objects on Earth, some of the objects are very heavy. However, water is very light. So what happens is, when the moon is at this angle, we pull the water on Earth. Say for example, this is our lake. Now this water will also be pulled towards the what? The moon. I hope you can really see that. And now with that, since the water, if this is our water body, assuming this is our water body, and the moon forces, the force of the moon is attracting in that order, it means that the water will move sideways, and maybe the water will move. And that explains why you find that it's believed that under the sea, water is always moving. That is it. Now what if when the moon is, now that one will give you, if the moon is in this position, if the moon is in that position there, that one will give us what we call a low tide. So if the moon is in this position, it will give us what we call a what? A low tide. A low tide. In a way that the tide, now a tide, those are large water masses which always move. So some people refer to them as waves. Anyway, you call them as waves. Those large water masses which are always moving in a certain direction. Those who have ever stayed near lakes, I think you can really figure out on what I'm trying to bring out here. So as this one pulls, this water level, the water in the water bodies will bulge or will move towards the moon like that, and therefore shall have low tides, because as this is our water body, the water will be pulled sideways in like that, and that explains why we have water always moving underground. Then what about when the moon is at this level here? When the moon is at this level, the moon will pull the water levels in that direction, and guess what will happen? Are you seeing this is our water body, but due to the gravitational pull of the moon, are you seeing the moon is pulling in that order? So are you seeing how the water is bulging upwards like that? So the water pretends as if it's going up due to the force of attraction, and now this one here will hence give us what we call a what? A tide. Just imagine it has risen up, and maybe you are here in your boat. Of course, there you just said the last prayer unless otherwise. So that's the kind. So the pull from the moon onto the waters on Earth will lead to the what you call the tides in the seas and the oceans. I hope that really makes some sense. Let's go there and find this in writing. Okay. So parent A, we want to remind parent A that please, these tides are brought about by the gravitational pull on the Earth by the moon. Okay, we said the rise and fall of water level is termed as tides. okay, which are caused by the gravitational forces of the moon and the sun on the earth's water bodies. Okay, the version of experiment on the moon will apply on the sun as well. Okay, the moon's gravitational pull, the moon's gravity pulls the water towards it, creating a bulge. Now a bulge means a swelling, like that is a bulge. That is a bulge. Okay, creating a bulge or a high tide, okay, on the side of the earth facing it, on the side of the earth facing it, yeah. Then on the side of the earth opposite to the moon, the earth moon rotation round a common center creates a centrifugal force which causes another bulge. As the earth spins, its different locations pass through these bulges, experiencing a high and low tides. So they're like, I want to have this explained again using these pictures. So here they're like, as the moon is pulling over this side, like that, okay, we shall have a bulge towards that side. But again, just as you are pulling, as this one is being pulled in this direction, sorry, let me resolve this. Okay, so as the moon is pulling in one direction, what you must know is that the earth and the moon are all rotating and moving. I don't know if you can really figure out that. So as the earth is rotating, even the moon is also rotating. The moon rotates around the earth. So that as it is rotating, what you call a centrifugal force is a force which comes in. Like say for example, as this water is being pulled right here, okay, as this one is being pulled right here, okay, so as this one is being, okay, as the moon is pulling the earth toward this side, there will be what we call a centrifugal force. Now do we have, if you have this is the center, like this, okay, a force which acts towards the center of a circle like that, this one here we call it a centripetal. It is a centripetal force. Then also, if you have a circle like that and you have this is our center, the force which acts away is what we call a centrifugal force. A centrifugal force. A centrifugal force. So centrifugal away from the center, centripetal towards the center. Okay, good. Now, as this one is pulling away like this, okay, then this one is pulling away like this, we shall get another effect, which is also acting in the opposite direction like that. But this effect comes as a result of as a result of Earth orbiting around the center of gravity between it and the moon. So the center of gravity between the moon and this one is like this, like that. So what does it mean? It means that as the Earth is moving upward, just imagine that, I don't know how I can make this move, but just imagine the Earth is rotating in this order and also coming down like this. And that effect moving up and down, rotating, like if it's rotating, I don't know how I can get this described, will also create a centrifugal force this side. As if now this water, as this Earth is moving, just imagine if the ball is rotating in this order like this. Okay, let me do this. If the ball is rotating in this order like this, like that, you realize that the air on the acting on the ball will be moving in that direction there. Anyway, I don't know whether that can make some sense, but we have it right here that the effect of centrifugal force on the ocean as a result of the Earth orbiting around the center of the orbiting means rotating around the center of gravity between it and the moon. Center of gravity between it and the moon will be maybe somewhere right here like this. So the Earth rotates in that order. Just imagine the Earth is rotating and this is the rotating point here like this. As it is rotating, it creates a centrifugal force which acts away from the center like that. That centrifugal force will give us a high tide. This side where the moon is pulling from will give us a high tide. An example is right here, that bulging we have. And now, if they have a high tide this side and high tide this side, the areas of Earth which are here and here will experience low tides. Okay, like so for example, if this is our ocean, that is a high tide. And of course we have a small one. So this one here is a high tide. And this small one here is a low tide. I hope that really makes some sense. Okay. Alright, good. So that's why here they told you that, read some ink. They say that on the other side of opposite the moon, the Earth moon rotation around the common center creates a centrifugal force, a force away from the center of the earth, which causes another bulge or a high tide. It means that when we have this is our earth, high, wherever force is acting here like this, high tide, then in these areas low tide. Okay, as the earth spins, so as the earth rotates, its different locations pass through these bulges. Like, what they're meaning is, as the earth is experiencing a high and low tide, meaning that as the earth is spinning, when the earth, okay, spins, okay, maybe this is point A, point B, point C, and point D. Now originally point B and point C are the ones experiencing high tides, and point A and point C are experiencing low tides. So if this point also moves and comes here, and point C reaches here, whereby point C comes there, point D comes right here, point A comes right here, and point B comes here. It means that again point C will experience a high tide, and point B also will experience a high tide also. Anyway, hope that really makes some bit of sense. Let's proceed again. We are done with part A, Roman number 2. In fact, not yet. We must go to, there were two parents, we must go to parent B. What did the parent B tell us? So let's go to parent B. Erase. Okay, parent B. So parent B said, how is it possible for someone in Uganda to talk to a relative in USA through a phone call, or a cell phone? Like, is it possible to be in Uganda and you make a call in USA and you talk to someone right there? Yeah, it's very possible, I think. Let's go and help out this parent of ours. All right, good. So with this still, we are going to go pictorial a little bit. So that is parent B. Let's go pictorial a little bit. Now, it all begins with, now let's assume our parent is even a mother or a woman. Okay, so, okay, is a woman and maybe is making a phone call. Here is our phone. Okay, now you realize that as this person is making a phone call, what first of all happens? As this person is speaking the words will be trapped by the phone. And what happens is, now don't first of all think about this. Now as the words are trapped by the phone, what happens inside the phone is, the phone has got a phone has got a chip which converts your voice into what we call electromagnetic waves. Now these electromagnetic waves are sent onto the antenna, and now this antenna here will send these electromagnetic waves to what we call, you can call it a telecommunication mast, to come right here. So from the phone to electromagnetic waves, from electromagnetic waves to the antenna, from the antenna to this, and from there to this, just like you're seeing directly there. Now what happens, remember we are now going right here. So let's come and give the reasoning. So assuming this is the woman right here, and what has happened in the phone you have explained, and now from the antenna towards the, okay, what we call the first earth station. We call it earth station, though locally people call them telecommunication masts. So when you make a call, it will come on that telecommunication mast, which we call the earth station. We then from there, as it reaches there, remember here it is moving in electromagnetic waves. Why electromagnetic waves? Is because electromagnetic waves are very light and they can move through a vacuum. Your voice cannot move through a vacuum. A good example is, if you are just right there and you try to speak to someone 1 kilometer away, cannot really hear you. So your voice is very heavy, it can't move through a vacuum. So what happens is, we need it converted into an electromagnetic wave, and that is done by the phone. Okay, inside, this is the inside part of the phone. Now from there, as it reaches the telecommunication mast or first earth station, it will go upwards onto a satellite up in the air. Just know that we have got satellites up in the air. If you don't know anything about this, please, about satellites, I'm going to put for you a video here which explains more about satellites. At the end of this video, I'm going to put you a video there, and you learn more about what we call satellites. But satellites, we have them up in the air, up, you know, a satellite by now. So the signals will be sent upwards, which we call uplink, upwards onto the satellite. Now this satellite, what it does, it boosts. Remember, they came as electromagnetic waves, but the satellite must boost them and convert them into recognizable what? Data. As the satellite has finished that, it will now send them downlink towards another telecommunication mast in the area of the person you're calling. If you can see here, a telecommunication mast in the area, maybe here, this has been our Uganda, and this is maybe our USA right there. So the mast will pick it and send to the phone. Now the phone also, the antenna will receive it. Now the antenna will now convert the electromagnetic waves sent forward into a voice, and the person will be able to hear. Okay, as simple as that. I hope that really makes some sense again. Now, what we call uplink to is that whatever this person again makes a call from America, it goes back the same way. This one boosts, again it comes one downlink, and this person will pick. It is a vice versa. Now, I know someone is asking, but again, how comes I'm able to call on a certain number and the phone number rings just on somebody's phone, not just, okay, if say for example you have called someone with a number you have saved in your phone, how comes it can just reach directly on that person, yet in the area where that person is staying, there are very many phones? Okay, it all starts with this. We have what we call a mobile switching center, the MSC, the mobile switching center. Now, one of the mobile switching centers in Uganda, we have MTN is a mobile switching center. We've got Airtel. Airtel is a mobile switching center. We have got Laika Mobile is a mobile switching center. Meaning that this mobile switching center has got a code, or your number registered by their company. So when they call, you see the mast which is right here. Yeah, the mast. Now this is the mast right at their place, but just know MTN will have very many earth stations in different places, if you can really think about that. So that earth station there is coded into a certain mobile switching center, maybe MTN. So when you call, it will be sent to that earth switching center, which is controlled by this MSC, the mobile switching center, so which has your number registered. So this one here will now allow a call directly onto your phone, because the phone number on there was registered in your names with this MSC. Hope that really makes some bit of sense. However, if you're a student, this may not necessarily carry sense. I've only brought it for your own understanding. All you must know is just keep on to this right there only. Okay, let's now go and have it written. Alright, good. So we start off. They're now saying that when a person makes a call, the phone sends a microwave signal to a geostationary satellite orbiting the Earth. Yeah, I talked about a satellite there. Okay, the satellite then amplifies the signal since they are weak. Yeah, I told you the satellite amplifies and retransmits the signals to the receiver's phone, which we call another stationary Earth station on Earth. Okay, receiver's phone in the USA connected to a global communication network. Now this talks about what we call the MSC, the mobile switching center, registered with what we call global communication network. Okay, when the other person speaks, the message travels in the similar process, enabling the global call. Like this is what we're meaning by uplink to. Like you can see here, that fine, you have called when you have called it goes like that. The uplink, we are seeing uplink, the one in pink color here, going uplink, in green color going downlink. That's when the person hears. When this person speaks, it follows uplink to via this one in green downlink to. I think uplink. Okay, oh, this will make some sense. So this one is taking one and this one is taking two, meaning that if this one speaks, follows the one uplink one, downlink. Okay, this was meant to be downlink one. First of all, uplink one, downlink one. That is the person to receive. Now when this one speaks, uplink two, downlink two. That's what really happens right there. Okay, now the geostationary satellite is what we call this one here. What they call geostationary is because these satellites, when you try to view them using another satellite, they appear as if they're just in one place, of which the word is stationary, meaning something which is just in one place, or a body which is not possessing kinetic energy, or a body which is not in motion. And that gets that explained. Hope the parent has really understood and has really enjoyed this straight away. Let's still proceed to another part, and that is, here we are, part B. Part B, remember I had our part A Roman number is done for parent and parent B. We got part B that's saying describe the life cycle of a star. By the way, before you go to this, you need to first of all, okay, yep, smile. Just know it is really interesting. Okay, let's go there without wasting time. How does a life cycle of a star come about? Life cycle of a star come about. Part C, or rather part B, life cycle of a star, as simple as that. Now it all begins with these guys here. A life cycle of a star begins with these two guys here. Please, I will just request that you be a bit keen about what we're going to bring here. Now, a star comes out. Where does a star come from? Now we have what we call the first stage is called the nebula. Sometimes they call it stellar nebula stage. These are scientific terminologies. We can't translate them here locally. So now the star comes from the cloud of dust and gas. But this dust and gas, just to inform you, is made of what we call helium atoms and hydrogen atoms. This is dust and gas. Now the clouds of dust and gas in there, just imagine a dust and gas circulating up in the air, and we call that a cloud. Alright, good. And it's just in the picture, just like you can see there, more like a smoke, but not really smoke. Okay, now what happens is gravitational force comes and pushes these particles together, Now guess what will happen? Once pushes these particles together, they will form a cluster or something more like a solid, and that is what we call a protostar. A protostar is what we have right here. You can really see that here it was a bit faint. Here it's becoming thicker because of the gravitational force, which is pulling or pushing the clouds inwards. Now what happens next is this. After that, when you're in the protostar stage, what will happen here is that now what happens here is that now as the protostar stage has been formed, remember I had the upper protostar stage. Within the protostar stage comes a retaliation. There is a pushing force from within, the protostar stage. Now what happens is this gives us what we call it a main sequence star. Reason, we have a lot of things happening here. Now we have the force inward pulling outwards. A force from the center of the protostar stage is pushing outward, and as it is doing that, remember we have the inward pressure because of gravity, which had originally right here. Simple reminder. So remember we had this force already in place. We had this gravitational force pushing inwards. Here it is still acting there, still acting there. Now, but remember we said that inside here there is also a retaliating force outward. But please just know that as this is happening, a lot of heat is always produced. I mean a lot of heat, close to 1 million degrees right here. Okay. Now here what happens is as that force is pulling inwards, that is the arrow up here, arrows up right here, arrows up right here, arrows up right here. So the outward pressure will lead to what we call nuclear fusion, like that. Will lead to what we call nuclear fusion. Now nuclear fusion means joining together. Reason why are they joining together is that, just believe it or not, that the gravitational force or the inward force will be stronger than the outward force. But I told you that this happens with a lot of energy or heat generated. Now what happens is that now in this stage where we are, that as here the outward force is pushing, but you have the inward force due to gravity pushing inwards. But just know that gravity is more, gravitational force is greater, so the inward force takes over. Therefore that will lead to what we call fusion, or joining together of those particles to make it a more solid. Now what we call one of the stages of a star is, did you know that the sun we see is also a star at a certain stage, which we call the main sequence stage? So our sun is also, in some billion years to come from now, our sun will also become a star. Anyway, a bit interesting. Okay, we proceed. So after that, just know that in the next stage we are going to proceed. Somewhere nuclear fusion will stop. We have it right in this stage here. So nuclear fusion stops, meaning the particles have stopped joining each other. What does it mean? It means that when nuclear fusion stops, we still have our inward pressure due to gravity and outward pressure due to fusion, or anyway outward pressure due to the reaction within the particles of the star. And I told you at this stage, this is what we have as our sun. At this level, this is what we have as our sun. Now what should you think? At this level, the next step is a bit controversial to what you are expecting. Now, do you know that we have different types of stars? Anyway, we got you covered. Let's get here. So what happens next is this. What happens next is this here, like this. Now, I explained this stage earlier on that the inward pressure is coming in. I've just pardoned the main sequence stage, still right there. Now, you realize that somewhere the nuclear fusion starts up again. Remember here, the inward pressure is again. Remember, the nuclear fusion had stopped again, still about the main sequence stage. So what happens here is that we still have the gravitational force pushing in and the inward force also pushing out. So what does it mean? This particle will start to expand again forcefully. It will start to become larger and larger. What does it mean? It means that the inward force is now greater than or has counterbalanced the gravitational force. So the particle is now becoming larger. And what happens here is takes us to two very good theories. Like, say for example, we say what comes next depends on how big the initial star was. Like from what we began with, the nebula stage we began with, was it very small or was it very big? This gives us two different answers from the main sequence stage. And of course, guess what? If it is big, if it is small or medium, we form what we call a red giant. Now, why a red giant is because it reflects a red color, just like you're seeing there. Just a change in color transits from the main sequence to red giant. That is if it was very small. Okay, let me resolve this. That is if it was very small, the nebula stage the one we began with. But if the nebula stage was very big, then we form what we call the red supergiant. Take note, we are all still about the main sequence stage, which is right here. If it was very small, we form the red giant. If it was very big, we call a super. Of course, super is big. Red supergiant. Now, what happens next is we describe this on its own, and we describe this on its own. You have to be steady right here. And of course, we move to begin with the red giant right here. Now, what happens to the red giant is that this is the red giant here. Maybe I try to highlight this for you. When it's it's medium, we form a red giant stage. Why red? It's because it appears red. Then it forms the red supergiant. They only vary in size, but they have the same properties. This one is small, this one is big. That's why I have the red super. But red giant is there, red giant is right there. So they complete their life cycles in different ways. Yeah, this one follows a certain path, and this one follows another path. Just like you see in a family, you're all born by the same parent, biological father, biological mother, but not all of you will have the same. Not all of you will have the same behaviors. Hope you can really look into that. So also happens to the star. So from here, they are all from the same mother, main sequence stage. Medium, red giant. Really big, if it is very big, super red supergiant. Now guess what comes next? We start with the red giant. Here we go. Now with the red giant, what happens to it is simply red giant, it now becomes unstable. We are meaning the particles within are at a very high temperature, and at this point we no longer have some of the particles. Remember, we began with the helium and helium and hydrogen. So now at a certain point where temperatures are very high, the helium and the hydrogen atoms join together. They bond together because the temperature is very high. So here, this becomes unstable. Now it expels out its outer layer. Now just know that this one here will expel out its outer layer. Outer layer was now red. And after expelling out the outer layer now becomes this, which we call, it is a hot, dense, solid core, which we call a white dwarf. And that's its color. You ever seen a stuff of that kind, I guess? So we call it a white dwarf. But now if time goes by and this later cools down, it becomes black. This white is because maybe it was still hot, but when it cools, it becomes a black dwarf. That is from the red giant. Remember, don't forget, we had it right from here. So red giant has given us, this red giant here has given us a white dwarf and a black dwarf. We are remaining with the red supergiant. What are we going to get there? Let's go there. So trying to get there, I'll resolve this. Trying to get there. Okay, let's get here now. Okay, this is the separation to these two guys. So this is a bit separate from that. Okay, now here, our big star, the one which was very big, what happened is it was our red supergiant. what happens is that more nuclear fusion takes place, meaning more particles will be joining together. Just see the color, it's now becoming yellow. So several cycles of expansion and contraction happen. So it can expand and meanwhile contract. Now that is as a result of the gravitational force versus the inward force from within. So this will now come to this, it will burst and give a flash. You have all ever watched a movie. Just imagine when a bomb is exploding, we call that a supernova. That kind of flash given out, we call it a supernova. So a supernova forms elements heavier than iron ejected across the universe. So supernova will split, flashing away, throwing away most of the particles. All the particles will fly into the air. I've told you, imagine when a bomb has blast. Now what happens here, after this blasting like this, two things come about. The more light particles will form what we call a neutron star, and the more heavier massive particles will form what we call a black hole, if you can really see that. So meaning that the red supergiant gives us a supernova. From a supernova splash, it will give us a dense core which we call a neutron star, and another one which we call a black hole. Okay, here gravity is able to pull in any light that passes nearby. Now what you call a black hole, you have all ever heard of that? A black hole is, just imagine on the ground, then you have a small hole. You have all ever seen a small hole, maybe a small hole for these white the black ants. If we try to look in there, are you able to even see light within? Not really. Now that's an example of what you call a black hole. A provisional example, I'm not saying that it's the real one in real life, but more a resemblance of what we call a black hole. And now this black hole is believed that whatever enters there does not come back, not even light. So if light if light goes there, cannot even come back, what about if a human being is thrown within there? By the way, now please, maybe just to make a simple figure out for you, we have what we call the stars and galaxies. A star is by far bigger than the sun, bigger than the earth, and bigger than anything you've ever thought of. I hope that really makes some sense. So because some people just be like, but the stars are smaller than the earth. Not really. Not really. The star is more bigger than any other thing here. Okay, so up in the air we have the solar system, we have the galaxy, or yeah, what you call the space physics, the stars and galaxies. There's also another world, the up right there. So there we are finished with this. So the red giant forms white dwarf, black dwarf. The red supergiant, which was big in size, goes into a supernova, and from a supernova to a neutron star, and from a neutron star to a black hole. Now a supernova is a blast, like an example of like a bomb blast. When a bomb blasts, just no particles will spread away. Now the particles with the larger masses will form what we call a black hole, and the particles with lighter masses will form what we call a dense, or rather a neutron star. I think I've already got that explained. Let's move. Now of course we can get you in summary just right here. The summary just right here. So we have our dust gas goes, they are compressed by gravity to form a protostar, and the protostar further inward force versus gravitational force gives us what we call a main sequence star. Here, this is where we have the outward force versus the inward force as a result of gravity. Now as we reach here, we form two things, red giant and super red giant. Red giant goes to white dwarf and black dwarf, all those are stars, and supergiant will split into supernova. And supernova is more like that flash you see after a bomb has blasted, we call it a supernova. Now from a supernova we form a very big star which we call a neutron star, and something very heavy. This one is big but not heavy. Now this one here is small but very heavy, which we call a black hole. Okay, so after figuring out on this, let's now go and look at this in details. Let's go there and look at it in details. We got some problem here, but no problem. Let's go there and look at it in details. So in details, we have it right here. Alright, good. So you look at that, you realize that when trying to go down at the explanation we gave we realize that we have this saying that stars begin their lives as vast cold cloud of gas, mainly of hydrogen and helium atoms, and dust known as a nebulae. Nebulae is a plural. The dust, the name for the dust right there, we call it nebula or stellar nebula. Okay. Now, a gravitational force triggered by shock waves from nearby supernova. Supernova is more like if you have something like this and it bursts and it spreads away particles. That's what we call a supernova in simple terms. So, okay, nearby supernova. So the supernova, solar winds or galactic collisions causes regions within the nebula to collapse inwards. Okay, but here you can even just talk about one. You can say shock waves. Shock waves within the nebula can collapse inwards. So that's the gravitational pull we talked about, or we had in the picture when we're beginning. Okay, as the cloud fragments collapse, it spins faster, causing its central core to heat up due to gravitational energy conversion, forming a protostar. Okay, this is where fusion takes place. We talked about fusion when they join together and form something more solid compared to what we began with. So when the core temperature becomes high, the core temperature is, if you have this, the particle, the inner part is what you call that. So it will start pushing outward. So when the core temperature becomes high, about 10 million Kelvin, that's too much, nuclear fusion starts, where hydrogen fuses into helium nuclei, meaning that the hydrogen will be bonded together with the helium to form a nuclei, and it will be a helium nuclei. Okay, this releases enormous energy. I told you of that. It releases a lot of heat, creating outward pressure that perfectly balances the gravity. Now that outward pressure, I remember when I was having the diagram, I was telling you there's that outward pressure versus gravity. And first of all, balance, then hence stabilizing the star. Now there's a point where the gravitational push inwards is equal to the outward force from within the core. So when they balance, the star will be, it means that hence stabilizing the star at that stage. So this is the 90% of the star's life. Now what you're talking about here, every stage from the cloud to the protostar, it can take a very many years, close to maybe it's a lot, more like maybe 1 million years from one stage to another, because I told you that even our sun we have is on a certain stage of, it's the stage of a star. Our sun is a stage of a star. It's hard to believe, however, it's a bit true. Okay, now 90% of a star's life, meaning that a star stays in that protostar stage for very many years. When the inward force, like what I'm meaning, this is we have the nucleus within, the inward push like that is equal to the gravitational push outside. There's most of the stars, that is the where the star stays for so much long. Okay, so maybe if they decide to stay for 1 million years, okay, maybe I'm just giving an example. If they decide to stay for 10 years, then you realize that all of the 8 years it spends it in that protostar stage. Okay, and our sun is in this phase. Okay, now protostar stage, and it gave us what we call the, okay, it gave us what we call the, okay, it gave us what we call the main sequence stage, where our star, protostar and main sequence stage, they are more like the same. What makes the difference is there is that gravitational push inwards and that outward force from within, which is counterbalanced to form what we call a stabilized star. And we said most of the star's life stays within there. Okay, now when hydrogen fuel runs out, remember it is hydrogen which is burning up, fusing or joining together with the helium atoms. So when the hydrogen fuel runs low, that is if the star has stayed for some good years, the core contracts, meaning the particle we had will contract. Okay, heats up, all right, causing the outer layers to expand and cool. So the outer layers will expand and cool, turning the star into a red giant. So due to the heat, the star will expand and become red. Hence we call it a red giant or a red supergiant. Clarified on that. Now what happens next depends on that. Remember I said that a red giant gives us what we call A red giant gives us what we call a white dwarf, and later a black dwarf. And a red supergiant gives us what we call a supernova, and right away to the black hole and the neutron star. So you're saying that the helium and the heavier elements start fusing in one core, ending as a white dwarf, neutron stars, or black holes. White dwarf is for the red giant. You can rewind the video and look at the pictures right there. Okay, that's game down already. Let's go back and see. Let's go back and look at this. So you have successfully answered the part B. Successfully answered the part B. Finished. We're going to part C Roman number 1. So part C Roman number the saying help towards establish the average density of the sun. Average density of the sun. Now to get this, you're going to base on this. Okay, let's go back here. To find this, you're going to base on this. Let's go right out here. So here they told us that, okay, so we had this, that the sun is 109 times, the sun's radius is 109 times the earth's radius, meaning that if the sun radius is rs, will be equal to 109 times the earth's radius. That will be our first equation, number 1. Another one is the sun's mass, m subscript s, will be equal to 3.30 times 10 exponent negative, exponent 5, the mass of the earth. That's Roman number 2, meaning that we have ms is equal to 3.30 exponent 5 me, this is e, and rs is equal to 109 re. That's what this means. The sun's radius is, that is equal sign, is 910 times means you multiply, so you have your re, means that there is a hidden multiplication. So you go look at these two here and you make an analysis. Don't forget that the sun and the earth is a sphere. What you call a sphere is something of this kind, please. Something in this shape is what you call a sphere. Allow me first of all draw this in that format, then we have it completed. A sphere is always in that form. A sphere is always in that form. So the volume of a sphere is right here, where need be we shall be using it. However, let's first of all go and look at that. Okay, good. Let's go there. Alright, good. So we first of all make the summary. Now we are saying that here, we are saying that let rho s be the density of the sun, where you see s density of the sun, ms be the mass of the sun, vs be the volume of the sun, and pe be the density of the earth, me be the mass of the earth, and ve be the volume of the earth. Okay, good. Now having reached there, remember we had from the statements that we had the statement right here that the sun's radius is 109 times that of the earth. Please, what you should know, this calculation is a logical calculation. You can't really find it directly in your notes, but you just get to know the approach we use here, because we have this statement in the question. But how do you use it? Now from definition I gave you this. It was that rs, sun's radius, is rs, is means equal sign, 109 is that, times there's a hidden multiplication, the radius of the earth. Remember, radius of the earth is re, since small e means earth and small s means sun, meaning that rs will be equal to 109 re from the statement we have right there. Then also we had this, another equation was that the sun's mass is 3.30 exponent 5 times that of the earth. Okay, how are we going to write that? Okay, now mass, we're going to use m, s for sun, me for earth. So we go there. So ms is equal to 3.30 exponent 5 me. That is our equation 2. It means that we are going to use these two equations here to get our answers. But what do they want? These people want density of the sun. They want density of the sun. But how shall we get that? We are going to play around with these equations to get our answers. I've told you that you may not have learned about this as a student in physics, but you just need to understand this right from here, such that you are not out of sight if in the case that really happens to appear in the forthcoming exams. Okay, And with that, without wasting time, now which one are you going to begin with? Which one are you going to begin with? Now you all know that we must begin with this one. Reason, the volume is given as 4 over 3 pi r cubed. So the volume has r in it, of which volume doesn't have mass. So we begin with this inclusion first of all to have this harmonized. And with that, let's begin off. So now we are going to say that assuming the sun and the earth are taken as perfect spheres, meaning the sun is a sphere and even the earth is a sphere. Please, we are just taking an assumption because we have a certain group in the United Kingdom who believe themselves, they call themselves the flat earthers. For them, they say that the earth is flat, not a sphere, as it is said. So it is allegedly said the earth is a sphere, and it is allegedly said the earth is flat. Who knows what is the truth here? Okay, so but as of now we know the earth is, that's why I'm saying that assuming, we ain't sure about that. So let's, I think, proceed right away. Now after doing that, if the sun and the earth are sphere, perfect spheres, then you have a right to use this formula here, that the volume of a sphere is given as this. Volume of a sphere is equal to this, 4 over 3 pi r cubed. Now what about volume of a sun? Volume of a sun will be 4 over 3 pi r radius of the sun. Are you seeing it within there? And even have it right here in this Roman number 1. Up there we're moving. Now with that, we shall separate that right there. Then we substitute within. Remember, rs is equal to this. This implies that, mirrors of this, where it implies that where you see rs, you have a right to put away this rs, and in place of that rs, you can put this guy here. So let's do that. So vs will be equal to 4 over 3 pi 109 re, but power 3. Where there is rs, we put this guy since they are all equal. Hope that will make some sense. Then with that harmonizing, we shall get, when you cube this, we shall get this. There's a hidden multiplication in between here. We have it right there. Now a 4 over 3, we are separating them. A 4 over 3 pi and this. Okay, allow me first of all of this. So we are getting this and this all at once, and even this one separate. But remember, each one of them must have a power 3. A power 3 on that and a power 3 on this. So we have it right here, times a 4 over 3 here. But now here it is the radius re squared, re, which will be having that power 3. Okay, there we are. So but also you have to remind you that, what do you think about the volume of the earth? Since here we got the volume of the sun, don't you think I can get the volume of the earth, so that you can get this also harmonized? So volume of the earth is given by, use the same approach. Where there is s, we shall put ee for volume of the earth. So to be b is equal to 4 over 3 pi re cubed. So does it mean here? It means that we are going to substitute in within. We're going to substitute here, and we see the way forward. But look at this. Are you seeing that what we have as an multiplication here, 4 over 3, from simplifying this up, 4 over 3 pi r e cubed is the same as this? Do you see that they're the same? Yeah. And if they're the same, you have a right to say that in the place where they are, you can easily put ve. So and that will become that you have vs, which you have right here, equals, which you have right there, 109 power 3 we have right here, and we have right there. So this whole guy here means ve, because the formula is 4 over 3 pi r cubed, then here 4 over 3 pi r e cubed, which you have. So it means that vs is equal to 109 power 3 times ve. It's more like a substitution. Please, you need to have some algebra here, and also, okay, be very keen and steady in this area here. Okay, we proceed. So remember, we have this expression already. Vs is equal to 109 power 3 times ve. Let's go in the next part, and we have this done. So again, to remind you that we had that in the other first in their previous part. So vs is equal to 109 power 3 ve. Remember, we want density, but you all know that by definition, density is equal to mass over volume. Anyway, is that true? Yeah, I think so. Now let's consider we have Vs. Remember what density of the sun. So shall we say density of the sun will be given by mass of the sun over volume of the sun. We have volume of the sun right here. Hope you can really see that. So we can now go ahead and substitute. So we shall say that volume, now mass of the sun, just to take you back here, we have mass of the sun as this. We have mass of the sun as this. Mass of the sun is the same as this. So where there is ms, you can just put this right here. You can just put what I'm circling right here. Only 3.30 exponent 5, and just we have it right here. I've made it that ms is equal to this. Okay, now we're going to substitute. Ms is going to come right here, and Vs is going to come right here. Vs is there, Ms is here. I've reminded you almost each and every part. Remember, this part wants us to get density of the sun, which is rho. Please, the symbol for density is rho. Rho, which is like that, more like letter P, and it's written as this, rho. Okay, I wish you really get that noted. So PS rather the rho s will be equal to, I told you we're substituting this, you have it right there, over 0.9 power 3. Now I have ME over VE. Do you really see that? ME over VE. Do you think this can have any meaning? Let's do the next step. Okay, so we are now saying that all right. Okay, let me first harmonize this. I think there's a technical error here. Allow me first of all harmonize this and get this explained. Okay. Okay, so let's get there. Okay, here we are now. So realize that when you substitute here, you multiply this ME over VE. You can simply have it as a multiplication. Remember, there's a hidden multiplication right there, there's a hidden multiplication right here. So it means that you can have this the way it is right here, and so to have here a hidden multiplication there, then the ME over VE is what we have right here. We want to have its meaning. Okay, but the density of the earth is the same as mass of the earth over volume of the earth. Do you see that? So in the place of this, you're going to substitute this. So now we shall say it is density of the sun will be equal to, we have this digit right there, this digit, this one depicted from this meaning here after substitution. But again, we must remind you that from the question they gave us that, okay, from the question they gave us that PE is equal to 5,500 kilograms per meters cubed. That's the density. So you're going to substitute here and you have it multiplied. Okay, you can rewind the video and look at the question. We had this already given to us. Density of the earth is assumed to be that. So after reaching there, you are getting it harmonized. You realize that when you compute this whole stuff, press in your calculator, you must practice how to use a calculator. The answer will come up with will be this, which will be approximately that. As simple as that. So density of the sun will simply be that. Okay, hope that really makes some bit of sense. With that, let's look at the very and last part. The very and last part, let's go there and look at it. Okay, so this last part here, we have it right here, which says we give the importance of studying astrophysics. That why do we study space physics? Why do we study space physics? Just imagine if the NASA did not step into studying astrophysics, space physics, where would we be so far? I guess even the phone you're using right now, would not be existing, because some of them use satellites for acquiring that network. So let's go and look into that. Why do we study astrophysics or space physics? Let's go there, and here we go. Okay, let's have our answers straight away, and we say bye-bye to this item. Okay, good. So here we now have, let's have this explained. Okay, they're saying, first of all, it helps us to understand our place in the universe. Like issues about the star, issues about the moon, issues about the sun, we would not be knowing much about what is up in the air there. But with the space physics, there we go. So it helps us in protecting technology and space infrastructure, like from solar flares and space weather. Yeah, we have some good technology. Guess what? By studying space physics, people were able to come up with what you call the, of course, you all watch football from the Star Times, uh, DSTV, even the television, the televisions, the TV stations we have in Uganda, all use satellites, which satellites are up in the air, which we got by after studying the science up right there. So advancing fundamental science and technology leading to innovations. Yeah, we have good innovations. We have the spacecrafts, you know that. So understanding the Earth's climate and environment using satellite and space observations to monitor global systems. Yeah, that's why you see that your phone is able to tell the weather or the temperature of a certain place. Of course, they use satellites, which satellites were put up in the space, which we call space physics. All right, this ends here. I would like to say simply thank you. Okay, may God bless you all. See you again.